Hi, welcome to this lesson about multiple regression. In the previous lesson, you learned about the linear regression model. This regression model allows you to predict one variable from another. For instance, performance from engagement. However, what if you want to use multiple variables? And there's more to performance than just engagement. That's going to be the topic of this lesson, so let's get started. Although a linear regression is a good starting point, there are often times where you want to see how multiple independent variables predict your dependent variable. For instance, turnover intention, the attitude of employees regarding leaving the company, which is often measured in engagement surveys, is a complex variable to predict. It relies on more independent variables than just engagement. In the previous lesson, you learned about the role of trust, but it can also be predicted by tenure, how recently someone was promoted, management style, and more. How do you go about performing such an analysis? This is where you use a multiple regression. A multiple regression is used to determine a mathematical relationship among a number of different variables. In other terms, multiple regression examines how multiple independent variables are related to one dependent variable. Once each of the independent factors have been determined to predict the dependent variable, the information on the multiple variables can be used to create an accurate prediction on the effect that they have on the outcome variable. If it's a multiple linear regression, the model creates a relationship in the form of a straight line that best approximates all the individual data points. With the linear regression analysis, you had the formula of y equals ax plus b. In the multiple regression analysis, this simply changes to y equals a1x1 plus a2x2 plus a3x3 plus b. Here, a1x1 is the regression coefficient that measures a unit change in the dependent variable y when x1 changes by 1. The same thing applies to a2x2, a3x3, and so on. Again, y is the dependent variable, and a stands for the different unstandardized beta values that the regression analysis produces for each of the independent variables. Now, these independent variables can be either positive or negative, depending on their effect on the dependent variable. For instance, if we take turnover intention, engagement might be negatively correlated with it, as high engagement is associated with lower turnover intention. However, the degree to which people are micromanaged on a scale of 1 to 10 can be positively correlated with turnover intentions. The more people are micromanaged, the more likely it is that people want to quit. In your regression analysis output, you will find two beta values, the unstandardized B or beta and the standardized beta. The unstandardized relationship is expressed in terms of the variable's original raw unit. If you would use the number of education years to predict annual pay, every year of extra education could add $2,500. In this case, the unstandardized beta coefficient will be 2,500 as for each increment of one raw unit, in this case year, projected earnings would increase by 2,500 raw units, dollars in this case. Standardized results, or standardized betas, have been converted into z-scores. As you've learned, z-scores convey information in standard deviation units. In this case, every increment in z-scores would produce much less than $2,500 as these increments are much smaller. Standardized results help us to compare the impact of the different variables with each other. The regression line that's produced in a multiple regression is linear. However, it is possible to test exponential models as well. One technique to do so is to insert both the linear line by adding the variable and then the exponential version by squaring the original variable. If the exponential line is a stronger predictor than the original linear line, an exponential relationship can be assumed. These are advanced techniques, so make sure to check available resources before drawing conclusions on this. Now, in the previous lesson, I explained how the R-squared can also be seen as the goodness of fit measure for the regression model. Since this is a multiple regression analysis, we can use the R-squared again, right? Well, not entirely. The R-squared has a number of problems with a multiple regression. Problem 1. Every time you add a predictor to a model, the R-squared increases, even if due to chance alone. It never decreases. Consequently, a model with more terms may appear to have a better fit simply because it has more terms. Problem 2. If a model has too many predictors, it begins to model the random error in the data. This condition is known as overfitting the model and it produces misleadingly high R-squared values and lessened ability to make predictions. In regression analysis, overfitting a model is a real problem. An overfit model can cause the regression coefficients, p-values and R-squared, to be misleading. An overfit model is one that is too complicated for your dataset. When this happens, the regression model becomes tailored to fit the quirks and random noise in your specific sample, rather than reflecting the overall population. If you drew another sample, it would have its own quirks, and your original overfit model would likely not fit the new data. Instead, we want our model to approximate the true model for the entire population. Our model should not only fit the current sample, but future new samples too. Suppose you compare a 5 predictor model with a higher R-squared compared to a 1 predictor model. Does the 5 predictor model have a higher R-squared because it's better? Or is the R-squared higher because it has more predictors? This is where we use the adjusted R-squared. The adjusted R-squared is a modified version of R-squared that has been adjusted for the number of predictors in the model. The adjusted R-squared increases only if the new term improves the model more than would be expected by chance. It decreases when the predictor improves the model by less than expected by chance. The best way to look at the adjusted R-squared is to look at stepwise regression analysis. With stepwise regression analysis, you continually add or subtract a new variable to your model. This will create different models, each with their own adjusted R-squared. It works as follows. Suppose you have some set of potential independent variables, from which you wish to try to extract the best subset for use in your regression model. These are the variables you will select on the initial input screen. The stepwise regression lets you either begin with no variables in the model and proceed forward, adding one variable at a time, or start with all potential variables in the model and proceed backward, removing one variable at a time. Each step, or model, generates its own statistics, such as the t-statistic, p-value, R-squared, and adjusted R-squared. Like I said earlier, R-squared will always increase, whereas adjusted R-squared does not necessarily. Here's a small example of an output that looks at the R-squared and the adjusted R-squared for each additional variable. The adjusted R-squared can be tested on statistical significance. This is usually the best metric to determine the validity of a new model. If the change in R-squared is statistically significant, it's a safe bet that the added variable adds sufficient explanatory value to remain in the final results. As you can see, the R-squared increases the more variables you put into the model, starting at 72.1 with one variable, up to 89.9 with 5 variables. The adjusted R-squared, however, peaks at 3 variables with 85.9. The last 2 variables decrease the adjusted R-squared to 80.7, meaning that the last 2 variables don't add much to our model. With a stepwise regression, the statistical program can determine which of the variables you want to use as input variables for your dependent variable will create the highest R-squared. Let's take a look at an example of a multiple regression analysis. Say you're interested in predicting the job performance of employees. You anticipate that several factors will have an influence on job performance, namely IQ, motivation, and the amount of social support they receive. Your model will look like this. All factors have a range from 0, very low, to 100, very high, whereas IQ has a mean of 100 and a standard deviation of 15. You let your statistical program of choice, here we use SPSS, to run a multiple linear regression analysis. The main result is shown here. If you remember correctly, our formula for our multiple regression analysis is y equals a1x1 plus a2x2 plus a3x3 plus b. To fill out these numbers, you have to look under b. The constant 18.13 is our b. The outcome of the IQ test has a coefficient of 0.27, motivation has a coefficient of 0.31, and social support has a coefficient of 0.16. Putting this in our formula, we get job performance equals 0.31 times motivation plus 0.16 times social support plus 0.27 times IQ plus 18.1. Using this formula, you can now predict someone's job performance when they fill out these questionnaires. Brilliant! However, you may also want to know which of these variables will have the most impact on your dependent variable from a standardized point of view. That way, you can more accurately know which of these variables you should focus on in either recruitment or training. By changing the unstandardized beta coefficient into standardized coefficients, by subtracting the mean from each variable from each of its values, and then dividing these new values by the standard deviation of the variable, we get the following formula. Job performance is 0.52 times motivation, plus 0.25 times social support, and plus 0.47 times intelligence. A minor note here is that the aforementioned constant has been left out of the figure. After standardizing all variables, it's always 0 because z-scores always have a mean of 0 by definition. To run a multiple regression analysis yourself, your test needs to adhere to the following assumptions. First, your dependent variable must be on an interval or ratio level. Second, the relationship between the independent and dependent variables is linear or exponential. You can test this by looking at the scatter plots of your data. Third, the multiple regression analysis requires that the errors between observed and predicted values should be normally distributed. Fourth, multiple regression assumes that there is no multicollinearity in the data. Multicollinearity occurs when the independent variables are too highly correlated with each other. Why is multicollinearity an issue with regression? Well, the regression equation is the best fit line to represent the effects of your predictors and the dependent variable and does not include the effects of one predictor on another. To solve this, look at which variables are highly correlated with each other and remove them accordingly. An example is age and overall tenure. These two variables tend to correlate highly as people enter the workforce at a similar age and also quit the workforce at, again, a similar age. In my own experience, I've seen age and tenure correlate with Pearson's R that was larger than 0.95. In this case, it's best to remove one of the two. I would use tenure in the analysis as that is more related to work situations compared to age. Fifth, you can't have any significant outliers, as your regression analysis is sensitive to outlier effect, similar to the linear regression analysis. The last assumption of multiple regression is homoscedasticity, similar to the linear regression. The variance of the residual in your analysis should be constant across your predictor variable. A scatter plot of residuals versus predicted values is a good way to check for homoscedasticity. Once your test adheres to these assumptions, you can perform a multiple regression. That's it for this lesson. In this lesson, you learned more about the multiple regression. Specifically, you learned how to use the statistical analysis, you learned more about the adjusted R-squared, and you learned more about the assumptions necessary to run a multiple regression. In the next lesson, you will learn more about logistic regression, which is often used when analyzing drivers of employee turnover. See you there!